Uh, Thanks for having me. So my name's Corey Arnold. I'm an assistant professor in the Department of Radiology, and I'm going to talk a bit about some of the work we've been doing on using topic models to explore biomedical free text. And so I just wanted to put this up there. I think this session is interpreting clinical data. So this is the clinical data that we work with, which I would argue is the most clinical of the data we've seen so far, and probably the most frustrating. So this is just a radiology report. And so frequently our task is to figure out how can we derive useful signals from data that looks like this for doing things like disease modeling with patients. So I'm going to talk a bit about topic modeling. So topic modeling is a completely unsupervised process by which we're going to try to derive some signal from this data rather than the plethora of knowledge-based solutions that encompass natural language processing and ontologies and terminologies. So briefly, what is topic modeling? It's an attempt to define statistical models that understand context. And in general, how do we do that? Well, we define topics as multinomial distributions over words. So I've just shown a couple of them here. So you can see the width of the black bar denotes the probability of observing that word in either the finance or the nature topics. And you can see that the word bank is actually ranked highly within both topics. And so the model has learned to understand that there are different contexts in which the word bank may be used. So topic models typically are generative models if we're talking about latent Dirichlet-based models. And so we need a way to actually model documents as well. And we'll just do that as defining multinomial distributions over our topics. So documents are now mixtures of these things, okay? And I'll note that each word is actually assigned a topic, and that can be important because these things are useful for things like document clustering, for deriving contextual features if you wanted to do something like document classification or phrase classification or information extraction, named entity recognition. You don't want to accidentally classify the Foley catheter as a name rather than a device, right? So you want contextual features that can tell you the different ways in which medical terms are used. Summarization and prediction. And so on the right here are just kind of two simplified drawings of topic models. Unshaded nodes are unobserved variables. They're sort of parameters defined by the model. And the shaded nodes are things we actually observe. So in this case, words and documents. And so here we have this model of GIST. So this defines how documents can be generated. And in order to generate a document, we sample this model to get some distribution over topics. And then we can sample words from those topics. So we might look up here and say, well, this is the finance topic. Let's take a word. So the seminal model in topic modeling was latent Dirichlet allocation that was published by David Bly in 2003 and his mentor, Michael Jordan. Although there were previous approaches like latent semantic indexing, but those didn't really put a prior on the topic space. So you can see, we don't need to go too much into detail with this, but the generative story here is that D is the number of documents in your collection, N is the number of words in each particular document, and then you have K topics that you've specified. So in order to generate data, you first take a sample from a Dirichlet distribution that's parameterized by alpha for each document. So now we have some multinomial theta D, so that defines the mixture of topics within the document. And then to generate actual words, we sample this multinomial. So if we have 10 topics and we sample this, we'll get some index between 0 and 9. And then we'll go up here and we'll say, okay, give me topic 5 or whatever we sampled, and we'll generate a word from that. And by this process, we can generate documents and entire collections. This is kind of the story I just told. The nice thing about using a Dirichlet is it's the conjugate prior to the multinomial distribution, so it's easier to parameterize given a data set. And that's just the probability density functions. So here's a simple example. How do we fit these models? Well, there's some variational inference techniques, but MC methods are a lot easier to understand. So here's a collection of 16 documents and 5 words, and we're going to say that there are 2 topics within this collection, our finance and our nature topic, if you couldn't tell by the words on the top. So what we do is we randomly initialize each word to one of the topics, and then we run our Gibbs sampling procedure and reassign each word one at a time. And this is the basic equation for how we do that. Essentially, you assign a topic to a word based on the probability that that word occurs within that topic times the probability that that topic occurs within a document. And all these things are derived just by counting the number of times this word has already been assigned to this topic. So if we run this for 64 iterations, we can see that very soon we already learn how words correspond or how they should fall into different topics. And so, right, the words that, or the documents that only contain finance words are all about the black finance topic. The words that only contain nature words are about the nature topic, and then you can actually mix topics when they contain both sets of words. Okay. So we want to use this in clinical data to derive some useful features or build some interesting applications. Here's just an example of fitting a LDA model to 500 brain cancer patient records. So you can see some of the topics here. And so these patients have surgical resections, and then they often have multiple imaging studies after resection to follow up on what's going on. They have biopsies, chemotherapy plans. And how might you use this? Well, one way could be you could look through the topics, and if something's of interest, or maybe you're searching for something in particular, like care plan, which is something that might not have a traditional index term or be difficult to do a keyword search for potentially. You can find all the documents that talk about a patient's care plan and highlight the words within those documents. So this is useful in large online data sets. We've worked with a couple of pharmaceutical companies that were very interested in what people were saying about their drugs online and their diseases online, not surprisingly. So we looked at rheumatoid arthritis. We just looked at one forum with 2,700 users, and we fit, I think, 150 topic model to that data set. And so, for example, you can see this sort of price concerns topic comes out, and if we want to look and see what that corresponds to, we can pull up related posts, and the words seem to match the topics, meaning just some other examples: infection and sickness, pain treatments, and I apologize for the ridiculous amount of significant digits here. That's what the model spit out, and I didn't want to go line by line and cut them off. Pain treatments, physician communication, so information sharing. So there's a lot of people that are saying, hey, look at this website I found, it could help you. There's a lot of people saying, hey, does anybody have a website that can help me? And then disability claims. So a lot of people wondering how they're going to pay for their very expensive treatment. What other way could we use this potentially? So we're working on building a summarization interface for primary care physicians. So right now, if you go see your primary care physician and it's been a couple years, he or she might go through your list of reports and quickly click one, scan through it, click the next, scan through it. So for healthy individuals, that's not a very tedious process, but for somebody with a very long or complicated disease history, that becomes a lengthy process, and the clinician tends to just be looking at the screen while you're sitting there wondering what you're doing, or they're trying to talk to you while they're looking at the screen. And so there are a lot of studies on how this can be frustrating and can lead to medical errors and things like that. And so we're working on an interface to try to extract the important semantic themes from the free text reports and display them to clinicians in kind of a timeline view. So this is a breast cancer patient, and you can see she has a breast cancer topic that's sort of consistent over time, but then there are new topics that emerge and go away, things like maybe there's pain that she received treatment for, or some persistent cough. Okay, so maybe I've gotten you somewhat excited about using topic models, and if I have, probably the best tool to get started with is a piece of software called MALLET, which stands for Machine Learning for Language Toolkit. So we didn't develop this. This was developed at UMass Amherst, but we have extended it in several ways for use in the clinical domain. So it's Java. I think there are R topic modeling packages, and certainly Python. So it does all of these things: clustering, topic modeling, information extraction. It's text focused, so all the values stored in there are discrete. You're not going to have a continuous feature. How do you run it? Well, after you download it, you can run a binary just from the command line and do some simple things. There's also a Java API, which is very useful, and you'd probably want to go that route if you're interested in using the software. Again, so see, these are some of the models. Today we'll talk more about the LDA models. So how does it work? Well, you model sequences, in this case documents, as binary feature vectors. And each sample in your collection is what's referred to as an instance, and these things can be kind of confusing in the beginning. An instance has a name, so every sample in your data set can have its own unique name. It has an input vector or something you're going to transform into an input feature vector. It has a target or a label, so in topic modeling we don't often have these, but there are supervised topic models. It has a source, because you're going to do a lot of transformations on your input data, right? You might do some rescaling or some normalization. And all these fields are defined as objects, so if you know anything about Java, that should tell you that it's a very general framework to work with. We don't assume any like integer types or double types or anything like that on any of these fields. So how do you actually get your data into the software? Well, you read lines, so they have tools to iterate over files. Then you do some tokenization. So you have all these things stored in this pipe object to transform your data, and you have an array list of pipes. And here's an example of that. We don't need to go through it. So then to model your data, it's as simple as saying, create me a parallel topic model. So this is a version of the model that just optimizes over the cores in your processor. And you have to specify the number of topics, and then you estimate the parameters. You can then evaluate it by getting a marginal probability estimator from the model. So you might write in with these types of models, we compare models by looking at the log likelihood of a held out test set. So in order to do that, you could get this estimator, give it a testing set, and it'll spit back the log likelihood. You can do inference too, so you could give it, we have a nice trained model, we like it, we give it some new documents, and it spits back what it thinks the probabilities are for topics in that document. Okay, so there's a lot of different types of topic models. There's topic models that combine with regression models to do things like matching authors with topics. There's models that attempt to translate language. There's models that incorporate time. So we built this kind of crazy model to better represent the clinical domain, where we have metadata associated with each patient, so things like gender and age and things like that, and metadata associated with each document, like who wrote the document, what was their specialty. And then we also have some special things in there to allow us to learn n-gram topics. And I'd be happy to share that code with anyone. It's not quite releasable, I wouldn't say. And then you can always build your own. There are very good model fitting algorithms in the code base. So, questions?